Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. The parallels between my supercomputer and an internet is this. My supercomputer encircled a globe that has a diameter of 8,000 inches. The internet encircled planet Earth that is a globe that has a diameter of 8,000 miles. Both my supercomputer and an internet are global networks of processors. The difference is that my supercomputer, that is an internet, is constructed systematically, while the internet grew incrementally and organically, and grew at different times and places. For this reason, namely the lack of uniformity and regularity, the internet as we know it today cannot be the hoped-for planetary-sized supercomputer that could ever be harnessed to find answers to the biggest questions facing humanity. If such a planetary-sized supercomputer can be constructed by our descendants, they could harness it to solve their grand challenge initial boundary value problems, such as those governed by the primitive equations of meteorology and other geophysical fluid dynamical problems arising in their extreme scale computational physics. Please allow me to describe the eureka moment that I discovered, namely that practical parallel processing will bring into existence a new supercomputer that will replace the old vector processing supercomputer. That was the moment that I understood my constructive reduction to practice of the massively parallel supercomputer to be the vital technology that must underpin every supercomputer that will be manufactured in the future. It was 8:15 in the morning of the 4th of July 1989, and across a new internet that was a new global network of 64 binary thousand processors. Each processor was akin to a tiny computer. I was speechless because I had recorded a previously unrecorded supercomputer speed of 3.1 billion calculations per second. I was shocked, and I stared in awed silence and disbelief. 3.1 billion is impossible, I kept saying to myself. My recording of that previously unrecorded supercomputer speed of 3.1 billion calculations per second implied that a general circulation model used to foresee otherwise unforeseeable climate changes that formerly took 180 years to run at computer speeds of 47,303 calculations per second per central processing unit can now be computed in only one day across a new internet that is a new global network of 65,536 central processing units. On the 4th of July 1989, no supercomputer scientist believed that I could parallel process 3.1 billion calculations per second and parallel process a grand challenge problem and do so across the slowest 64 binary thousand processors in the world. Shortly after my eureka moment, it made the news headlines that an African supercomputer genius in the United States has discovered how to solve grand challenge initial boundary value problems and how to solve them by chopping each problem into 65,536 smaller problems. I mapped those smaller problems in a one problem to one processor corresponded manner and mapped them to my as many processors. My experimental discovery of the massively parallel supercomputer made the news headlines because it was magic, wizardry, and science fiction back in 1989. Because practical parallel processing was then believed to be impossible, every vector processing supercomputer scientist that I told that I had parallel processed a grand challenge problem believed that I had made an embarrassing mistake. For 3 months, I also wondered if I had made an embarrassing mistake. In the 1980s, I massively parallel programmed 16 ensemble of up to 2 raised to power 16 processors that each tightly encircled a globe. Each of my ensemble was a new internet that I visualized as my new global network of up to 65,536 tightly coupled processors that shared nothing. By the late 1980s, I had programmed more processors than any person that ever lived. For a decade, the reality was that the potential to execute the fastest recorded supercomputer calculation and execute them across the slowest processors was on my fingertips. It took me nearly a decade, from the early 1980s to the late 1980s, for parallel processing to sink in and for me to gain the scientific maturity that I needed to solve real-world problems and solve them across my new internet that was a new global network of 64 binary thousand processors. My contribution to the development of the computer is this. I figured out how a new global network of 65,536 processors that outlined a new internet can synchronously communicate together as a virtual supercomputer and simultaneously compute together to yield a 65,536-fold jump in supercomputing speed. I was in the news in 1989 because I figured out how to make the impossible to compute possible to compute. The news headlines described me as the Nigerian supercomputer genius in the United States that figured out how to parallel process the toughest problems arising in calculus, algebra, and physics. My supercomputer wizardry resided in the never-before-seen manner that I programmed my 2 raised to power 16 processors. the new knowledge that I contributed to calculus, algebra, and physics. My supercomputer wizardry resided in the never-before-seen manner that my 2 raised to power 16 processors, that I programmed my 2 raised to power 16 processors. The new knowledge that I contributed to calculus, algebra, and physics is this. I discovered how to integrate the smaller pieces of a grand challenge problem and how to do so across a small internet that is a new global network of 65,536 tightly coupled commodity off-the-shelf processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing between each other. I was surprised to see that my invention of practical parallel processing meant a lot to many people. My world's fastest supercomputer speed struck a chord in people across Africa. In the 1980s, the words supercomputer and internet was not in the vocabulary of the African newspaper. It was then a novelty to read about a Nigerian supercomputer genius who was at the farthest frontier of human knowledge. It touched their nerves that I worked alone for 16 years despite the rejections. I invented practical parallel processing that in turn was a major invention of the 20th century. As a black inventor, I was not allowed to be the inventor of my invention. My processors, each akin to a small computer, did not program themselves. I hand-coded each computer with pinpoint precision and wrote its email primitives. I was in the news headlines because I parallel processed across my new internet that was outlined by a new global network of 65,536 small computers. Studying physics is not the most noteworthy contribution to human progress. However, contributing new knowledge to physics, such as parallel processing, is a noteworthy contribution to human progress. My contribution to physics is this. I discovered how to use the slowest computers in the world to solve the toughest problems in the world. I discovered how to solve grand challenge problems and how to solve them in a one problem to one processor corresponded manner, and how to solve them after I had chopped each grand challenge problem into 65,536 smaller problems. That supercomputer breakthrough that made the news headlines enabled me to solve in only one day and across my new internet what formerly would have taken 65,536 days or 108 years to solve on only one computer. I hand-coded my parallel processed solution to the grand challenge problem of supercomputing, and I did so to deliver the highest performance ever recorded on a supercomputer. At 8:15 in the morning of the 4th of July 1989, I was speechless when I saw the experimental results of my decade-long quest, namely the world's fastest calculation across my new internet that was my virtual supercomputer. To discover a new equation is to gaze across the millennia. My contributions of 9 new partial differential equations of modern calculus and to humanity's knowledge of mathematical physics and extreme scale computational physics was the culmination of a body of mathematical and scientific contributions that were made by my mathematical ancestors and made across the millennia. The oldest recorded contribution to mathematical knowledge was recorded 3,700 years ago. That contribution was written in a papyrus and written by Amar. African geometers such as Euclid, who is the father of geometry, were influenced by African arithmeticians such as Amar, who is the first arithmetician that we know by name. Amar lived 14 centuries before Euclid and lived in the same region, that is the valley of the River Nile in Africa. The introductory geometry that you studied as a teenager has its mathematical roots in ancient Africa. Geometry is the contribution to mathematics of ancient Africa. That mathematical contribution was historically preserved by Islamic scholars that studied in North Africa. That contribution was preserved across the ages and transmitted and built upon for thousands of years and along the 4,100-mile valley of the Nile that was the birthplace of Egyptian civilization. Fast forward 2,300 years from Euclid. For the record, Euclid was an African geometer, and there is no record that Euclid ever traveled outside Africa. There is no record that Euclid is not a black African. Fast forward from Euclid in Africa to 1989 to another African mathematician in the United States, Philip Emeagwali. I was the cover stories of top mathematics publications. My discovery stories were about my contributions of new calculus, new algebra, and new mathematical physics to mathematical knowledge. My contributions to mathematics began as a theory or as an idea that was not positively true and materialized as the world's fastest computer. Who invented the internet? I theorized a new internet that was a new global network of commodity processors that is a virtual supercomputer, or that could be used to build a new supercomputer that encircled the globe in the way the internet does. Back in the 1970s and 80s, I was mocked and ridiculed and accused of embarking on a grandiose and overreaching supercomputer research. I was mocked for wanting to solve that larger system of equations of a new algebra and solve it across a small copy of the internet that I invented. But on the 4th of July 1989, I figured out how to harness that new internet, which was a new global network of 64 binary thousand commodity processors. I was in the news in 1989 because I figured out how to use that new internet and use the technology to solve the toughest problems arising in extreme scale algebra and arising from the discretization of the partial differential equation, which is the most advanced expression in calculus and the most important equation in mathematics. Parallel processing must be discovered theoretically before it could be discovered experimentally. 9 in 10 supercomputer cycles are consumed while solving the partial differential equation of calculus. For that reason, to experimentally discover the parallel supercomputer is to de facto solve an initial boundary value problem arising in geophysical fluid dynamics and to solve that grand challenge problem across a new internet that was a new global network of tightly coupled processors that shared nothing, that encircled a globe in the manner the internet did. That was the technological achievement that gave rise to the question: did Philip Emeagwali invent the internet? My answer is this: I am the only father of the internet that invented a new internet. The entire internet that encircled the earth cannot be created at once or be invented by one person. I theorized my invention as a new internet, and I did so before I invented it as a new supercomputer that I used to parallel process and solve a grand challenge problem that could not be solved without the massively parallel supercomputer. As a lone wolf research supercomputer scientist of the 1970s in Oregon and District of Columbia, and of the 1980s in Maryland, Wyoming, and New Mexico, I had to understand what I was doing. I had to understand what I was going to do before I did it. It would have been impossible for me to send and receive emails along my new global network of 1,048,576 email wires and send to and receive from 65,536 processors. Each processor was akin to a small computer. It would have been impossible for me to send and receive as many computer codes and do so without my deep understanding of my new supercomputer machinery. Unlike the 25,000 vector processing supercomputer scientists of the 1980s that misunderstood that machinery as a computer per se, I understood my new virtual supercomputer technology to be a new internet that I visualized as a small copy of the internet. That technological vision of a virtual supercomputer that is a never-before-seen internet was uniquely mine. That contribution is the reason I am often referred to as one of the fathers of the internet. I conceptualized a new internet as a virtual supercomputer. But more importantly, it made the news headlines in 1989 that a Nigerian supercomputer genius in the United States had figured out how to harness that new internet and how to invent that computing machinery as the world's fastest supercomputer. On my eureka moment of 8:15 in the morning of the 4th of July 1989, I felt like I was struck by a bolt of lightning. That day, I became the first person to enter into a new territory of human knowledge called practical parallel processing. A common misunderstanding is that a scientific discovery is teachable and that a technological invention is learnable. To discover is to know something that was previously unknown. For that reason, you cannot teach what is yet to be discovered or what you don't know. Nor can you learn something that had never been seen before. The first person to do something did not learn that thing from the second person to do that thing. I did not learn how to parallel process across processors. I invented the supercomputer that parallel processes across processors and simultaneously processes a million things at once. When you are the pioneer of the new parallel supercomputer that can do a million things at once, there is no parallel supercomputer scientist to learn the then non-existent technology from. I am the first parallel supercomputer scientist. In the 1980s, I was the only full-time programmer of the most massively parallel processing supercomputer ever built. That is the reason to this day I am the only person that published a full-breadth lecture series on his contributions to the development of the modern supercomputer that parallel processes across processors. I am the first parallel supercomputer scientist. I did not learn how to parallel process. I invented the parallel supercomputer, and I did so by being the first person to figure out that the parallel supercomputer is a million times faster than the vector processor that is not a member of an ensemble of vector processors. As an inventor, my dilemma was akin to that of the first person that flew an airplane. Nobody taught that first person how to fly the first airplane. The first pilot did not have a license to fly. As the first parallel supercomputer scientist, I had to have a deep understanding of my never-before-seen supercomputer. I had to understand my supercomputer, both forward and backward. My command of those computers is the reason I have given impromptu supercomputer lectures and delivered them without lecture notes. The grand challenge problem of supercomputing was not a one banana problem. This scientific problem was listed by the US government as a grand challenge, and it was described as the toughest problem in supercomputing. My grand challenge was to figure out how I could harness the potential supercomputer power of the slowest 2 raised to power 16 processors that each had its unique 16-bit long email address. That email address was also its unique binary identification number. Each processor had its own dedicated memory that shared nothing. Each processor operated its own operating system. To believe that I solved the grand challenge problem by serendipity or luck is akin to believing that 2,300 years ago, 65,536 monkeys, each on a typewriter, bashed out Euclid's The Elements, that for over 2 millennia became the all-time best-selling mathematics textbook. At first, and in the 1970s, I visualized the grand challenge problem as 64 binary 1,000 pieces of a randomly scrambled puzzle. Each piece of that supercomputing puzzle had its unique 16-bit long binary identification number, or a unique string of 16 zeros and ones that was scribbled on it. In 1989, it made the news headlines that an African supercomputer wizard in the United States has figured out how to put that puzzle together. I am that African supercomputer scientist that was in the news back in 1989. In the 1980s, my grand challenge was to put those 64 binary thousand pieces of parallel processing puzzles together. I figured out how to put those 65,536 pieces of parallel processing puzzles together and how to do so in 16-dimensional hyperspace, and how to do so along 16 mutually perpendicular directions. The modern supercomputer is powered by about 1 million processors. Back in the 1980s, I was the sole full-time programmer of the most massively parallel supercomputer ever built. The reason I was the lone wolf was that I was the only person that understood the importance of the parallel supercomputer. That was the reason supercomputer scientists that won the top prize in supercomputing won it as a member of a team of up to 50 supercomputer scientists that were supported with $1 billion supercomputer. I was the only person that won that top supercomputing prize alone and won it as an outsider. The 25,000 vector processing supercomputer scientists of the 1980s abandoned parallel processing and did so because they did not believe that parallel processing should or could power a supercomputer. Who is the father of supercomputing? The father of supercomputing should at least believe in parallel processing that is, after all, the vital technology that now underpins every supercomputer. I am called the father of the parallel supercomputer because every supercomputer parallel processes, and I am the only father of supercomputing that invented practical parallel processing. I had to be supremely confident and know who I am, namely a research physicist that was at the frontier of knowledge of extreme scale computational physics, and also at the frontier of knowledge of the then never before seen massively parallel supercomputer. I was the supercomputer scientist as well as the internet scientist that broadened his agnostic invention and did so to make his contributions to the development of the computer and internet and to make them to remain as timeless and as evergreen as possible. Back in the 1980s, I was the lone blackface that attended 500 weekly research seminars. Each seminar speaker was a research mathematician or a research physicist or a research computer scientist. Each seminar speaker was visiting from Europe or Canada or somewhere else in the United States. For me to religiously attend and understand those multidisciplinary seminar topics demanded that I be a polymath that is at home in extreme scale algebra, partial differential equations of calculus, and the as yet invented massively parallel supercomputer. If I wasn't at the frontier of knowledge of those sciences, I would have discontinued attending those scientific research seminars, and I would not have been the cover stories of dozens of scientific publications. Prior to my discovery of how to parallel process across processors that shared nothing between each other, some research vector processing supercomputer scientists had a one-to-one conversation with me. They were impressed with my parallel supercomputer discovery in progress. From the 1970s through 80s, they were impressed enough to describe me as an up-and-coming supercomputer scientist to be watched. That was the reason 6 American institutions courted me and supported me with scholarships and fellowships, and did so for 16 continuous years onward of a scholarship letter that was dated September 10, 1973. After those 16 years of study and research in the United States, my confidence did not come from my winning the top prize in supercomputing. I won that prize in 1989. My confidence in my intellectual ability to work alone and to solve the grand challenge problem of supercomputing arose because I programmed supercomputers nearly every day of those 16 years. I programmed 2 raised to power 16 commodity off-the-shelf processors that encircled the globe in the way the internet does. I message passed or emailed across those 65,536 processors and across 16 times 2 raised to power 16 email wires. I programmed supercomputers for 16 years. On June 20, 1974, in Corvallis, Oregon, United States, I was programming the one-time world's fastest supercomputer that was rated at 1 million instructions per second. On July 4, 1989, in Los Alamos, New Mexico, United States, I discovered the answer to the grand challenge question of supercomputing. That grand challenge question was clear-cut, namely, how can I reduce 65,536 days or 180 years of time to solution on only one processor that is not a member of an ensemble of processors, to only 1 day of time to solution across a new internet that is a new global network of 65,536 processors. Put differently, the grand challenge question was, how can I compress 180 computer years into one supercomputer day? In 1989, I was in the news headlines because I provided the first clear-cut answer to that clear-cut question. I was in the news headlines because I articulated my discovery of the parallel supercomputer as a new internet that I visualized as a small copy of the internet. I articulated that new supercomputer with a clarity that was echoic retentive, and I did so when other supercomputer scientists were providing extremely nuanced and overly obfuscated lectures. Research computer scientists were committing the cardinal sin of publishing abstract papers that did not explain their contributions to the development of the supercomputer and their contributions to the ever-growing body of knowledge of modern computer science. In scientific research, the search is for new knowledge and not for a journal paper. Writing a scientific research paper is not the finish line, but for an academic, merely publishing a paper is his finish line. What is Philip Emeagwali known for? My discovery of practical parallel processing changed the way people perceive me. Parallel processing changed the way we think. Parallel processing is an entirely new approach to computer science and one that ushered a new era in supercomputing. Parallel processing was the technology that was mocked and ridiculed as a huge waste of everybody's time. Parallel processing is now the vital technology that underpins the world's fastest computers and that extends the boundaries of human knowledge. For me, Philip Emeagwali, my discovery of the parallel supercomputer was my stepping stone that enabled me to step from the serial and vector processing supercomputers of the 1980s and earlier to the parallel supercomputers of today. Those serial processing supercomputers became obsolete because they cannot be used to solve the toughest problems arising in abstract calculus, large-scale algebra, and extreme-scale high-resolution computational physics. The supercomputers of the 1980s cannot accurately solve many real-world problems because they only computed in a step-by-step serial or vector processing fashion instead of supercomputing in the radically different parallel processing method, or dividing the grand challenge problem into 1 million smaller problems and mapping those divided problems and solving them with a one problem to one processor correspondence and mapping them across an ensemble of 1 million commodity off-the-shelf processors that each operated its own operating system and that each shared nothing, and solving them at once or in parallel. Back in the 1970s and 80s, my massively parallel processing supercomputer research focused on making discoveries rather than on writing about theories. A theory is an idea that is not positively true. Each year, billions of theoretical papers are published within the field of computer science, with none contributing to the development of the computer. A vacuous theoretical article that was never read and that described no discovery is incentivized over a groundbreaking discovery. For that reason, the academic scientist lacks public stature. As a result of that publish or perish syndrome, the scientific paper became a distracting background noise. In 1989, I was in the news headlines because I discovered that parallel processing will become the vital technology that will make it possible for the supercomputer of today to be super. I discovered that parallel processing is the irreducible essence of the modern supercomputer. Parallel processing is the most important technology within the supercomputer. Parallel processing redefined the computer and enabled us to see the computer, the supercomputer, in a new light. Massively parallel processing provides extreme-scale computational scientists with the incredible supercomputing power that makes it possible to solve grand challenge problems that would otherwise be impossible to solve. With a market share of $20 billion a year, the parallel supercomputer is used to tackle the world's biggest challenges, such as answering the biggest questions arising in science, engineering, medicine, and business. From mathematics to physics to computer science, the supercomputing paradigm has shifted from the single processor supercomputer to the parallel supercomputer. My contribution to this paradigm shift was that I was the first person to figure out the immensely complicated procedure of dividing a real-world grand challenge problem into 65,536 smaller problems and figuring out how to distribute those 2 raised to power 16 problems and how to map them in a one problem to one processor corresponded manner that was nearest neighbor preserving, and how to map them to as many commodity off-the-shelf processors that outline and define a new internet that I invented. The grand challenges are the 20 biggest questions in computer science. Today's grand challenge questions are more complex than that of yesterday. The discovery of practical parallel processing changed the way geologists search for and recover crude oil and natural gas, and changed it from simulating on only one processor that is not a member of an ensemble of processors to simulating across up to 10 million processors that were tightly coupled to each other. Similarly, parallel processing changed the way the climate modeler predicts global warming and changed the ways the computational mathematician and the supercomputer scientist compute for the answers to their biggest questions. Parallel processing changed the way we understand computer science and changed the way computer scientists understand the supercomputer. Parallel processing changed the way we find crude oil and natural gas. In the old sequential processing way, the petroleum reservoir that is 1 mile deep and the size of a town is crudely simulated on only one isolated processor. In my new parallel processing way that I discovered on the 4th of July 1989, the petroleum reservoir is accurately simulated across millions upon millions of processors that were tightly coupled to each other. For the research scientist that asked, what if parallel processing extends the boundaries of what can be discovered? For the research engineer that asked, what's next? Parallel processing extends the boundaries of what can be solved. For the research mathematician that asked, what's next? Parallel processing extends the boundaries of what can be achieved. Thank you very much. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.